Hi, and welcome to our lesson 5 in our probability chapter. Today we're going to be looking at the multiplication rule for independent events, and we'll use some of the information that we did yesterday. So, I asked a couple of questions to a last year's AP Stat class, one of them, and in one of those classes, this is the information that I received. First off, I asked them what was their gender, and I had 12 girls, 14 boys. And then I asked them, do you regularly use eye makeup? Well, I got yes responses from 12 of the girls and no yes responses from the boys, which didn't surprise me a lot. Okay. Next, I asked them this: can you make Spock fingers? I wondered because I've never been able to make Spock fingers, and I love Star Trek. It's just not something I can do. But in that particular class, 10 of the 12 girls were able to do the Spock fingers, and 11 of the 14 boys were able to do them. So I want you to think about that for just a moment, and let's answer these questions. In the eye makeup poll, the first two questions, it was way more likely that a female used eye makeup than a male. Would you agree? Or you might say that gender had an influence on whether or not someone used eye makeup. A rather big influence based on my data. Gender had an influence on wearing makeup. Folks, if that's the truth, that makes those things dependent events. That is, you're way more likely to be a makeup user if you're a female. Or, another way of saying that, whether or not you wear makeup depends on your gender, at least in my data. With the other question, in the Spock fingers poll, gender really didn't have any influence. It seemed like both genders were able to do it. Gender didn't have an influence. Spock fingers. And that makes them independent events, folks. The outcome of the gender question didn't have any effect whatsoever on the outcome of the Spock fingers question. That makes them independent events. And the way that we find probabilities for dependent and independent events are different. So let's get a formal definition of independence here. Two events are independent if and only if, and we're going to do this symbolically, if and only if the probability of A happening is exactly the same thing as the probability of A happening given B did. I want you to think about that. The probability or the chance that A will happen is exactly the same whether B happened, right? And vice versa, the probability that B happens has to be exactly the same thing as the probability that B happens given A did. In other words, it doesn't matter if B happens. The probability of A happening doesn't change. The same thing is true. The probability of A happening doesn't change whether or not B did, or it doesn't matter. The two events are totally independent of each other. So there's the formal definition. I'd like next to talk about the formula for the probability of two independent events occurring. So this is another AND probability. And in probability always means multiply. So in the case of independent events, the probability that both happen, it's the probability that A happens multiplied by the probability that B happens. Okay. And then we've got a little problem here. Actually, this is a pretty good little problem. About 42% of people have type O blood. Suppose that you check, you pick two people at random, you check whether or not they have O blood. We want to make a table that shows all the possible outcomes. So we have person 1, and they either will have O or not. We have person 2, and they either will have type O or not. And let's see if we can't put some probabilities in here for these events. And then we'll look at some totals as well. But the probability that person 1 has type O blood is 0.42, because that's true for anyone. If I pick 2 people totally at random, then one person's blood type will not be affected by the others. That is, they're independent events. And the probability that we get an O and another O, that's going to be 0.42 times 0.42, which is what our statement said, is roughly, I'm going to call it 0.18. Okay, so we have a 0.18 chance of having both people have type O. The probability that person 1 does not have type O, well, if 42% of the people do, then 58% of the people don't. So the probability that person 1 doesn't, but person 2 does, this would be the probability of a not and an O. That's 0.58 times 0.42, according to this. Again, one's blood type is not affected by the other. That is, where they're not related, they're independent. So this is about 0.24. If you think about that, same thing would be true here. For one person to have type O and the other not is about a 0.24 probability. And for both of them to not have type O blood, that would be probability of not and not, 0.58 times 0.58, about 0.34. The probability that exactly one of the 2 people has type O blood, well, it could be person 1 and not person 2. Or it could be person 2 and not person 1. Okay, that sounds like a great big probability statement right there. It has an or in the middle of it, and person 1 and not 2. We know that because that's in our table. Person 1 does, but person 2 doesn't. That's a 0.24. And we add that to the other situation where person 2 has it, but person 1 doesn't. That's another 0.24. That probability would be 0.48. And we are asked here to make a tree diagram that illustrates that same situation. Every tree has to have a start. So here's the root of the tree. There are 2 events here. Choose one person. So here's my first person. And this person either has type O blood, which has a 0.42 probability attached to it, and I'm going to type in O right there, or that person does not have type O blood. There's a 0.58 probability associated with that. And you'll notice right there that those 2 things add up to 1. Each stage of the tree diagram has to add up to 1. Once we've selected the first person, then we pick the second person, and there are 2 choices for that person. He or she either has type O blood, and there would be a 0.42 chance of that happening. Now I'm going to ask you to think about this. There's also the chance that they don't have type O blood, and that would be 0.58. Have we added up to 1 there? We've taken care of both possibilities, right? That's good. If, on the other hand, our first person did not have type O blood, the second person still could with that 0.42 chance, or they could not with the 0.58 chance. And if you think about this, a tree diagram is a really good way for collecting all the information in a sample space. There are 4 possibilities here. Probabilities can be found for each of them by following the branches of the tree. So if we wanted to know the probability that we got O and O, we look at the OO branch and we see that we'd have to multiply 0.42 times 0.42, which we've already done. That was 0.1764. We have on this branch a yes and a no, and there are 2 like that. So the probability that we get an O and an N, there are 2 ways it could happen, and the probabilities along those branches are 0.42 and 0.58, which was 0.2436. And twice of that, 0.4872. Then we have one branch where it's a no and a no. So we can find the probability there by just following that branch, no, no. And we've already multiplied that one as well. 0.58 times 0.58 was 0.3364. And I would stipulate to you that for this experiment, we've covered all the bases, haven't we? Then all of these probabilities should add up to 1. And I will take just a moment and show you that that must be true. 0.4872 plus 0.3364 plus 0.1764 sum up to 1, folks. We've covered the entire sample space. We've accounted for all the probabilities there. Tree diagram is another way of showing what happens in the table. Okay. In fact, you're adding the same numbers. We've got all the bases covered here as well. So 0.1, well, we rounded, but 0.18 plus 0.48 plus 0.34. We're going to get to the same place that we did here. Okay? Add up to 1. The tree is sometimes a good way to organize your thinking, though. Sometimes I find it easier to make the tree than the table. Just depends. All right, we've got a couple of little practice questions that we want you to do here, and I don't think it'll take the calculator. So it says, suppose that we are rolling a single die and then we flip a coin. First off, are the events independent? Does what I flip on the coin affect what's going to happen when I shake the dice? And the answer is yes, they're independent. One has no effect. The outcome on one doesn't affect the outcome on the other. The outcome on the dice doesn't affect the outcome on the coin. So they are independent. And the probability that you get that 6 and then a tail, well, according to the rule, it'd be the probability of getting a 6. This is an AND rule and independent, so we multiply the 2 probabilities together. And our chance of getting a 6 is 1 in 6. Our chance of getting a tail is 1 in 2. There is a 1 in 12 chance that both of those things will happen. Very good. That's our lesson on independent probabilities. We'll see you in school tomorrow. We'll talk about this a little bit more.